Hello and welcome to my series on automation, the car company tycoon game. It's early access alpha release. The gist of the game is you run a car company and you have full control over your vehicle design and engine construction. I just thought I'd do a quick video, kind of explain some of the principles of internal combustion engines. I'm an engineering student and huge space nerd, but automotive is actually my area of greatest expertise at the current moment. So I just want to get into something I'm a little more knowledgeable about than the vagaries of space travel. This engine right here that I've created is kind of it's the best stab I've made at a F-body LS1 like you would find in a Camaro or a Firebird Trans Am. In those cars, they were actually derated from what they were in the Corvette. They had a more restrictive exhaust and a smaller camshaft, and so they only produced 305 horsepower versus the 345 that the stock Corvette was rated for. But I'll kind of break this down and explain things as we go in. It's a V-plane. It's a V8 with an aluminum block, and using this, I can strip parts away. From the factory, it came with a forged crankshaft that had a stroke of 3.622 inches. I had to kind of fudge on the bore, but this is actually the cubic inch displacement I got out of it, approximately 346, is as close as I can get by adjusting the bore here. The crankshaft is forged steel. I'm not entirely certain the stock connecting rods, just because I've got 178,000 miles on my Trans Am, and knock on wood, I haven't had to go inside it yet. I've always had big plans for it, but I really need to get my 1995 Honda Prelude finished and running before I can start getting into this engine the way I want. And because I'm not putting the Honda back completely stock, it's going to be a little beefed up. There's been a significant delay. Bottom line is my Trans Am is my daily driver, and with the current engine setup and my 273 rear gears, I get about 24 miles a gallon on the highway, and my job commute is all highway, so I'm really loath to mess with any of that, even though I've had a set of 313 rear gears that I've been dying to put in for years now. But that out of the way, it's got hyper-eutectic cast pistons, no fancy forged jobs from the factory here. But to get into crank theory, when everyone talks about stroke, they're talking about the distance from the center line of the crank to the rod journal bearings. And if you think of this journal as a lever, as you extend it, as you make this longer, you can apply more force. It generates more force from the same combustion event is the best way I can put that. There are limitations to that. Once you start changing the stroke, you automatically change to chain. If you lengthen this, you also have to put a longer connecting rod in it to keep your compression ratio and cylinder volume the same. Changing one thing in the bottom end always necessitates changing something else. Once you change that, because you're able to draw in more air, you have to put a bigger camshaft in that can open your valves enough to allow that extra air in. And as we add our connecting rods and then pistons, and bore is obviously just it's basically just piston diameter. You can go really crazy here, but as I said, this is a 346 cubic inch engine. And your rod journal length has a lot to do with your torque and horsepower balance, and I'm really going to get into that on another video because it kind of requires its own separate explanation. But we get into our top end. It is a boring old classic pushrod design, meaning your camshaft rides in the valley between your pistons, and these push rods ride along the camshaft as this elongated section of the cam rotates around. It lifts the push rod, which pushes against the rocker, which pushes the valve down and open. It's a very old design, very simple. Occasionally with extremely high horsepower applications, or due to a lack of lubrication, you can bend push rods and cause all sorts of problems there. But it's actually very reliable. I have a 1959 Ford Fairlane Galaxy 500 retractable hardtop that has a 292 Y block, which is also a pushrod engine. So even this goes back well into the 50s and before. We add our block. There's not a lot to say on head design. The major considerations when designing a head are flow, and that's basically your port size and shape. There's some things that go into combustion cylinder design, but all that is handled by extremely advanced CAD machines, and that's the realm of engineers today. You can, if you've got just a bunch of old heads laying around, it is still feasible for a just shade tree mechanic through trial and error to find a good optimal flow pattern, but it takes a lot of I guess folk knowledge would be the best way to put it. You just have to have kind of an innate understanding of how these things work and enough raw materials, because as you shave down these bores, you run the risk of running into water jackets, oil passages, reducing the strength too much where the head is in danger of cracking. But and there's also the exhaust port design. And so when people talk about a port and polish, they are literally talking about carving out some extra area here and then polishing more on the intake side, because exhaust doesn't care whether it's a smooth surface or not. Smoothing out the intake surface, which you can go too far if you have a mirror-like finish. The tiny imperfections in the intake port actually allow fuel vapors to collide with them and break up. And the smaller the unit of fuel that you have in there, the easier it evaporates for combustion. So if you go with a mirror-type finish on the intake port, you can actually reduce your horsepower and make combustion more uneven. It has a 10.5 to 1 compression ratio from the factory, which is pretty aggressive. But again, it's very reliable. I've got 178,000 miles on this engine, and once again, knock on wood, I have not had any major failures with the engine. I replaced the water pump at 80,000 because that's just kind of when they go. So I've actually been worried that I'm due for another one pretty soon. There's no variable valve timing. It's got a pretty sporty cam profile. I think this is actually a little aggressive, but this is in percentage. Go back to cam profile. A cam profile has two measurements. You have your lift, which is your distance from the center of the camshaft to the end of that, and basically that, you can imagine the longer that is, the higher it pushes the push rod and the wider it opens the valve. You also have duration, and this is a very low poly model, so it's not a good example, but duration is how long it keeps it open, and that's determined by this shape right here. A more oblong shape has more duration. Kind of a sharper edge is a lower duration camshaft, and that has to do with where you want to make your power, because this is all set in stone. There's no variable valve timing, variable valve lift on this car. You're tuning it for operation in a specific power regime. A high lift, low duration cam is very good for high speed, high horsepower settings, because it opens the valve as wide as it can, but it doesn't keep it open for very long, because at the higher RPMs your piston's going to be coming up faster, and if your intake cam is open as that piston's coming up, you're going to be driving air-fuel mixture out of the piston. So you want to get your valves closed before combustion begins. Again, this is really low poly, so there's not a lot I can explain. It's kind of a representation of a cam, but what I was getting at with this is just a percentage. You have full race at 100, and 78 is where I was keeping this one. I can't pick lift and duration individually on my camshaft for this engine. That's a concession to gameplay, because it'd be very hard to accurately and I guess reliably model lift and duration in the confines of a simple game without turning it into a piece of engineering software. Going here, nothing fancy, just naturally aspirated V8. Build this back up. Fuel system, it is fuel injected with multi-point fuel injection, and what that means is the injector hovers right here in the intake, just ahead of the intake port, and it sprays fuel right at the valve opening with the high velocity air coming from the intake to provide your mixture. Different versions of that are single point EFI, and this is basically just a carburetor with a single injector hovering right here. It's very simple, very basic. This is a carburetor intake manifold with just a few provisions made for modern electronics. Direct injection is something entirely different, and I'm going to get into that in another video, but direct injection is kind of the way of the future, and they kind of staged this as technology progressed. You had mechanical injection, which like the World War II German fighters, the Messerschmitt 109 and the FW 190 were equipped with. And the advantage of that over, say, the carburetors and the Spitfire was because they had constant fuel pressure. One of the easiest ways a ME 109 could get away from a Spitfire was just go into a shallow dive, because they had their fuel constantly pressurized and going into the tank or into the cylinders. They could just do a negative G maneuver all day long. The Spitfire and the Hurricane, as you dipped over, the negative Gs would lift the fuel up out of the carburetor bowl and starve the engine of fuel, and the only way to follow a Messerschmitt in that maneuver was to roll upside down to keep positive Gs applied, but it took so much time to execute this maneuver. We're in a situation where just seconds or milliseconds can determine whether someone gets away or not. It was actually a very effective technique for getting away from a Spitfire. You may recall that some of the more valuable sports cars from the 50s, specifically speaking of like 1959 Corvettes and even a few of the 57 Bel Airs, you could order a mechanical injection setup. That was not available, to the best of my knowledge, on any of the Fairlanes like my Ford, but I do believe Ford did some things with mechanical injection. I'm not as familiar with Ford history outside of what my specific Fairlane had. Then like I said, single point injection. This came around in about the 70s, and it was a nice stopgap before we got into multi-point. And you can actually have an electronic distributor ignition. The Nissan Xterra, the 3.3 liters early models, have a variable ignition distributor, which is pretty cool. But just kind of pointing out why this isn't an electronic ignition block. But multi-point EFI is what my Trans Am's LS1 is equipped with, so that's what this one's going to have. Has a performance intake. It's not a full race setup. It does have baffles and bends. Actually, it's a pretty straight flow in there to the engine. This, on the LS1 Trans Ams and Camaros, this intake comes straight forward to the core support. There's no bend, so you have extremely high velocity air coming in. This is tuned to run on 93 octane. which was available at the time these cars were made. Mine's a 1998 model, and it was only just a couple years ago that you stopped being able to find 93 octane where I live. It runs fine on 91, and if you put 87 in, it'll actually compensate and just flood the cylinder with more fuel to cool it and prevent pre-ignition. These are all things I had to set up for tuning, and again, the ignition timing they did as a percentage. In real life, ignition is measured in degrees before top dead center, and that's degrees of crankshaft rotation. So imagine the engine is set, and I actually think it is set at top dead center on the compression stroke. If this is 0, ignition timing, to advance the timing, you would be degrees before top dead center, and that is to, as the piston comes up, it takes time for that fuel mixture to burn, and by having an earlier ignition event, you can have it start right before your piston gets to its top dead center, and it'll have maximum expansion as the piston begins to come back down. And that's how you make power, and that's how you have a smooth, efficient running engine. But again, this is just in a percentage. It's not in degrees before top dead center, which it takes schooling and practical experience and a lot of stuff to kind of understand this in terms of degrees. So again, it's a gameplay concession. I think it's a pretty wise one because I am a gearhead, but I know not everybody really needs to or wants to get into the nitty-gritty of things. So exhaust is where they kneecapped my engine when they took it out of the Corvette to put into the F-bodies. Instead of having well-flowing headers, which that would not be correct. There. This is long tube, and that's something even on Corvettes you'd be seeing aftermarket. Tubular is, their model is off, but this is a typical header, and what a header is that it is a tuned length of pipe to maximize exhaust velocity out of the exhaust port. And you see that it's a very, very smooth transition. It'll be able to maintain its velocity out of there. When they put them in the F-bodies, short cast might actually be more accurate to my car. But cast log is easier for illuminating it, or illustrating. You see it comes out and there's immediately a 90-degree bend for all of these cylinders. That creates back pressure, and I'm going to eliminate this myth once and for all. Back pressure is terrible. There is no benefit to it. Anybody who says cylinders are scrounging for back pressure or what have you, they are talking out of their butt. Back pressure is the enemy. The point of exhaust design for making power is to keep velocity up, and this severely curbs your exhaust velocity because it comes straight out into a 90-degree bend, and then it has another 90-degree bend before it can evacuate. Now, my Trans Am, the F-bodies had better designed cast manifolds than these are. In fact, most cars do. Imagine this as a, say, 45-degree bend, and this moved back here at another 45 degrees. In modern cast manifold design, they've pretty much eliminated the 90-degree bend. But if I go to headers on this car, that's going to be cheating a bit. So I'm going to go ahead and change this to short cast. It's a single exhaust. That's another concession they made, because General Motors has it's a written rule. You cannot build a vehicle that outperforms the Corvette. The Corvette is the flagship sports car, and the humble F-body should not, from the factory, be able to touch it, unless you spend buku dollars on, say, like a 2002, back in the day, if you'd bought a 2002 Eliminator Edition SS Camaro, which very few of those were even made. My buddy's 2002 SS Camaro that we pulled out of a salvage yard and rebuilt, we didn't know it until we were done with it, but it was actually a very limited edition 345 horsepower SLP engineering SS Camaro. Most SS Camaros made 325 horsepower. This was essentially the Corvette motor dropped into a Camaro. It was one of the fastest cars in our group of friends, and when we get around to it, it will be again. It's just, it had a hard life after he tried to sell it. But that's an entirely off-topic rant. But yeah, Mustangs are typically fitted with a dual exhaust. This isn't how it's configured in the car, but in a Mustang, imagine they come together in an X pipe and then flow out the back as duals. But on the F-bodies, they had them feed into one collector and then run out the back of the car. 2¼ inch diameter stock exhaust, which actually this pipe right here is more oval shaped on a stock F-body for ground clearance issues, and that does the change in the shape. Although the interior volume is the same, the change in the shape does reduce exhaust velocity and once again chokes off power a bit. It's got a 2-way catalytic converter from the factory. My vehicle is still equipped with all catalytic converters and exhaust emissions equipment. There's only one muffler at the back. And here we can go and actually start and run the engine. And this is a manual test, and this is basically to figure out where your weak links are. As you throttle up, you see I'm getting a restriction in the muffler, and my pistons are having a hard time with the RPM. But I can shove it all the way up, and it's not something terrible, and I'm not losing, I'm not knocking or anything. And this is where naturally aspirated versus supercharged engines. A naturally aspirated engine will always be running at vacuum. There will always be negative pressure in the intake manifold. Even because of volumetric efficiency in a naturally aspirated engine can never exactly reach 100%. But with a supercharged engine or turbocharged engine, you're compressing the air and you're shoving more air than the pistons can themselves pull, and so that's what they call making boost, which 15 is about average for a production car. Large drag racers or Formula One cars, especially with the turbos, they will go well over 40 psi, but those are just, that's a level of nuttiness and we're not going to get into today. Switch back to test mode, and this is an automated test. And it'll just run it and get me my performance specs. And I guess I should have stuck with my cast log as far as the game was concerned, because 305 is actually closer to what, it's actually exactly what an LS1, Z28 or Trans Am, not Firehawk or WS6 or SS Camaro, not any of the really high-end ones. 305 is where they were limited to, which is still pretty impressive. I'm never wanting for power. But to kind of explain how a power graph works, and this kind of goes back to that old salesman pitch. People buy horsepower, but they drive torque. It pretty much makes me throw up in my mouth every time I hear that. But kind of explain what horsepower and torque are for those who are kind of shady on it. Torque is your instantaneous twisting force. That is how much force is being generated at the crankshaft at any given instant. Horsepower is a measure of torque over time. And so as your torque rises, your horsepower rises with it, obviously. But you see where your torque starts to fall off, but your horsepower keeps rising. That's because as your engine spins faster, you're generating more horsepower over time, because the exponential increase in your RPM, you're actually able to generate more torque over a given amount of time than instantaneously, if that makes any sense at all. And this isn't accurately modeled entirely because the LS1 I built, I have in real life. Peak power is made at 6,500 RPM and starts to fall off rapidly after that. So there's no point in trying to string these things out to their full 7,000. But just shorthand, easiest way to understand it: torque, instantaneous twisting force, and horsepower is torque delivered over time. So this was just my little introductory video to the automation engine builder. I'm going to do some other things, like I'm going to build a Honda VTEC motor and some forced induction things later. But I thought a basic push rod V8 that I'm familiar with would be a pretty good introductory video. So thank you for watching, and I will have another one up in the future.